I'm going to be talking about first light. So this is a very arguable term for the first stars to exist in our universe. You could say first light was the Big Bang. You could say the first light was the cosmic microwave background radiation. So I'm just going to pick one and say, well, first light was when the first visible light that lasted a while came into the universe. So I'm going to start off with a little bit of a segue and tell you all that I never actually wanted to be an astrophysicist. I'm just going to try and move this. There we go. I never actually wanted to be an astrophysicist when I grew up. I was instead obsessed with Egyptology, originally archaeology, but then Egyptology. And then there was one story which captured my heart unlike any other, and I think it's the same for every young Egyptophile, and that is the story of the discovery of Tutankhamun. This was in the 1920s, and what happened was Howard Carter on the left here and Lord Carnarvon chipped away at this tomb door that they'd found under the sands, and Howard Carter held up a candle to this little hole that they drilled in. And Lord Carnarvon behind him said, "What can you see? What can you see?" And Howard Carter just replied, "Wonderful things, wonderful things," and later wrote that everywhere all he saw was the glint of gold. So a story that still gives me goose pimples now because of the level of discovery, the level of finding something not just new, but something very old. And that is something that I took forward with me in my career because I study something new, which is an area which hasn't been covered much, as you'll see, but also something very old, which is the first stars to exist in our universe. And it was only through, well, teenage years, changing minds and coming across a book that spoke about special relativity that I didn't understand 95% of, but my mind was blown by the fact that physics wasn't just simple harmonic oscillators. And so I was like, I've got to go to university to study this. And what I like is that space and discovering our past within astronomy taps into this fascination we have as humans about understanding where we came from, both in terms of, like literally where spatially, but also where we came from in terms of ancestry. There's all these family tree programs like Who Do You Think You Are, etc., etc. And there's all these DNA kits, right, that supposedly tell you something useful. And when you're a kid, there's this kind of holy triad of the three pastimes as a kid, and two of them are really about history directly, which is archaeology and exploring lost tombs, and you've also got dinosaurs, obviously, who doesn't love dinosaurs, and then you've got the third one, which is inevitably space. So normally when kids think about space, it's the planets, rockets, but as astronomers we go much further than that and actually tap into something which is very exciting but not communicated to our younger people too well, and that's the reason I think that a lot of people do leave physics, but that's another talk. Okay, so I'm going to start by talking about what is light, because this talk is called First Light, and it's not very good if we're not understanding what we're actually going to try and observe and what it's the first of. Now, I'm sure you all know, because I think I understand that everybody in this talk, I think I understand that they are a student of physics or astronomy, but anyway, there is the electromagnetic spectrum, and this covers many different types of light. So whereas we use light in day-to-day conversation to mean just an optical wavelength range, so your reds, your blues, your oranges, greens, actually either side of that visible wavelength there are many more stretching outwards either way with different types of light. So you've got your radio light, you've got your infrared light that can kind of detect your criminals running away across fields on US cop shows. You've got your UV light, which can be used in CSI to find blood and things, and apparently in Ibiza to dress yourself up. And you can use X-ray lights, for example, which can, well, uncover all sorts of things, like in this one, a chest infection. And we're actually used to using all these different types of light in common usage. We're just not really used to talking about them in the different wavelengths. So, for example, if you broke your arm, you wouldn't be very happy with your doctor just looking at your arm and saying, yep, it's broken. What you'd expect is for them to send you to an X-ray to say, yes, it's broken this way, and this is how we're going to be able to fix it. Okay. Now, in space, we do exactly the same thing. We diagnose different things about our universe using different types of light. So, for example, here is a galaxy, doesn't even really matter which one. It is a nice halo of stars with a lovely dusty disk in the middle. So very, very average galaxy, nothing much to say about it. And this image is taken with optical light, visible light. Now, if we then turn a radio telescope to the same galaxy, then this is what we get. And what you can see here are very large, very diffuse radio jets emanating from this galaxy, in particular from the very center of this galaxy. Now, firstly, you've got a structure here that you had no clue about in optical light, because if you define your galaxy as the emission, you know, before you might have defined it as like where the light ends on the galaxy. Now you can define it by where the radio light ends, and suddenly this galaxy's got a lot larger. But secondly, and more importantly, when people sat down and they said, well, where can these radio lobes, as we call them, where can these radio lobes have come from? What could create this amount of energy to create radiation that emanates that far? And it turns out that pretty much the only mechanism that anybody can think about is a black hole, and in particular the accretion disk around a black hole producing a huge amount of radiation. Now, this mechanism isn't even well understood today, and it's not the thing I'm going to focus on. But what I want to point out is that using a different wavelength of light, we've managed to add information. And that's pretty handy, especially when you're looking in space and you're often in situations where things are very faint, invisible light. You're facing a situation where it's a very cloudy day, so you need a different kind of light to get through the clouds. There's lots of different ways we can use different types of light. And we really do. We have infrared telescopes, we have X-ray telescopes, we've got UV telescopes, we've got radio telescopes, optical. We really are using the full range here, which is very good. And the one thing that kind of brings together all these different wavelengths of light is the fact that they all have the same speed. And that is, of course, the speed of light, or 300 million meters per second-ish. And this has real implications for what we can do in astronomy, because even though it's very fast, it is finite, which means that it is extremely fast, but it's, well, I'm repeating myself there. It's finite, lovely. And what this means is that when you wave at your friend on the moon, for example, and they wave back, it takes around 2.5 seconds for the light to go all the way to the moon and all the way back. And so it's only 2.5 seconds. And so you wave at them, they wave back, you see it, you're happy, hurrah. And so it really, you don't really even notice the delay at all. And that's because the distance between the Earth and the moon is so small compared to the speed of light that it just zips back, you don't even notice it's gone. When you're looking at Mars, however, because of the extra distance between you, the light takes longer to travel over that distance. And so it takes 4 minutes to travel there, and it takes 4 minutes to travel back, by which time you've spent 8 minutes just waiting for your friend to wave back, and you're pretty miffed, and actually you've probably just walked off. Now let's go to one of our nearest galaxies. Let's wave at our friend in, for example, Andromeda. Unfortunately, it takes 2.5 million years for the light to get there, and it takes 2.5 million years to get back, by which time you're not just sad, you're actually very dead. And so this kind of example shows you why the speed of light is so useful, because it can let us look back in time, which is a phrase you often only find in science fiction, but it's my favorite thing to tell people, tell kids at an outreach thing. It is absolutely what we do on a daily basis, because the light coming to us from Andromeda is 2.5 million years old. So we see Andromeda as it was 2.5 million years ago. And conversely, if there is an alien researcher in Andromeda currently training their telescopes down to Earth, what they're seeing is not humanity as we know it right now, but what they're seeing is the Earth as it was 2.5 million years ago, which is when the Earth was populated by an earlier species of human. What is it? Homo habilis. I'm not an anthropologist, so something hairy, not us anyway. So yeah, and that just blows my mind that this can be true, that we can actually see something as it was actually happening. And what really brings it home to me is, I've thought about this, and it's kind of like, if you had a much slower speed of light and some clever mirrors, etc., then you could train your sights on Egypt now, and you could watch them build the pyramids, so you could figure out how it was done, and you would be seeing Egypt as it was 5,000 years ago or something, which it's awesome. I mean, the universe wouldn't work if it was like that, but I thought it was cool. So we can be pretty smug as cosmologists, where cosmologist we mean somebody that kind of fills in the large scales of the universe, both in time and distance. We're really interested in understanding the entire evolution, the entire lifetime of the universe of 14 billion years. And we can be pretty smug about that. We understand what happened really close by now. We can see Mars, we can see with the moon, we can see Earth very well. And as we go back, we can see light from Andromeda, 2.5 million years. We can see light from lots of other galaxies through the Hubble Deep Field. And so the Hubble Deep Field, for example, I hope everyone's seen this image before. If you haven't, go Google it after this, not right now, after this talk, please. But what this is an image of every light point in there is a galaxy. And there's an incredible diversity of structure and color, and it's just gorgeous. I have a giant print of it on my living room wall, which is one of the places I was meant to sit today, but for various kids running back and forth, I'm not. But what amazes me is that whole image was taken on a kind of like such a small diameter. It's about 1/10 the diameter of the moon, I think it is, on the sky. And so to think of that repeated all over the sky, and that's the kind of structure that there is just... and we can even skip right back to the start of the universe and be pretty confident about what happened. So yes, we can't observe the Big Bang for various reasons, because the universe wasn't transparent back then. But we can understand from lots of different things, so for example, the cosmic microwave background radiation, so literally the afterglow of the Big Bang that has been detected. We can see the expansion of space-time through the movement of galaxies. We've got it pretty nailed down. So the vast majority of astronomers are very comfortable with the entirely ridiculous idea that the entire universe in terms of space and time inflated and exploded and expanded from an infinitely dense point. But that's what theory and maths does for you. Even though it's completely ridiculous, it's completely believable. But what's in between? Well, that's what we're going to be talking about today. That's called the era of the first stars. Well, that's what I call it. And it lasts from around, it lasts for around 800 million years, a billion years-ish. We're very uncertain, to be honest, after the Big Bang. That's a pretty big chunk of the lifetime of the universe, and it's a time that we have very, very few observations of. In fact, we have one, which I'll get onto in a minute, and that only came 3 years ago. So this is a really, really new area and very, very exciting one to study. So the first question we can ask ourselves is, was there a first star? No, we're not. No, you know what? I'm not going to go through that today. Sorry. No, that sounds a bit weird, but because I've just talked about it. Was there a first star? Lovely quote that I'll let you enjoy. Oh. Lots still to understand. Lots still explore. Space is great. I've gone through the evidence for the Big Bang, so I'm actually not going to bore you with that. So the question is how did everything get from a universe which had just exploded in incredible heat, incredible radiation, incredible energy and violence, where nothing very large could be created very, very easily. So it's not like the stars popped out of the Big Bang at all. The only things that could exist in the early universe were the most simple of atoms, so hydrogen, helium, maybe a smidge of lithium if you're lucky. And you can build up higher things like that, like boron or carbon, but it will not be very long until a photon or another atom comes along, crashes into it, and knocks it over. It's kind of like trying to build a really big Duplo tower in a room full of sugar-crazed toddlers. The larger the taller the tower, the more teetery-tottery it is, and so even a slow-moving child is going to knock it over, and it's the same back then. So you've got a universe very, very simple, and yet you get to you get to a universe that is full of that diversity that you saw with the Hubble image. So there are first stars to go after, which is good. Now we need to understand why to care. I care because, well, I think it's really fascinating, and I'm amazed anybody pays me to look at this stuff. But there's other reasons to care. So, for example, as astronomers and as any scientists, actually, we're very aware that incomplete data can lead to incorrect conclusions. The pandemic's been an excellent advertisement of this, actually, because very early on we had very, very little data, and so there were so many incorrect conclusions given that it was extremely confusing. And now, as we've gone on, we're managing to hone that down, because the more data we get, the more sure we can be about it. So if, for example, an alien from Andromeda is trying to understand the human lifetime, so how do humans grow? How do they age over their lifetime? This would be one example track for a lifetime. You're a baby, you're a child, you might decide to have children and bring them up, and then you advance into your aging years, later aging years. But what if our alien is very hard pressed for time and research money, like researchers on Earth, and instead can only take a single sample? So maybe they go to a nursery, maybe they go to a nursing home, but that's it. And they miss out a whole area of the population. And they go home and they think about it and they say, well, hang on, I did hear somebody talking about a stork. Clearly, that's what happens in the middle. That fits my data absolutely fine. To the pub. And you can really easily see why that would happen. And so it scares me, and it scares many a cosmologist, that we are missing around 1 billion years of our timeline. And I can't remember if I've got it later on in this talk, so I'm just going to mention it now. And actually, when you look at the billion years that we're missing, if you take 1 billion years and you compare it to the lifetime of the universe, then it's actually the same. If you equate that to a human lifetime, it's the same as missing everything from the day that your child is born to the first day that they go to school. And if you consider how formative those years are, how much stuff happens, how important the growth is, and how much data you're missing on your child, you're missing so much fun and excitement and stuff that really affects them in later life. And I really believe it's kind of the same for the universe, in that we're missing the universe's first steps. We're missing everything. We're missing all the first things that happen to it. And for me, that's well worth looking at. The second reason to have a look, though, is that the first stars themselves are extraordinary. So they are extraordinary. They are not like our sun, as we can picture here. Our sun here is just nice and yellow and orange, as you can see, very nice. And what defines a star in general is that it's fuses lighter elements, so pushes together atoms that are very light, like hydrogen, fuses them together into a heavier element like helium, and in that reaction produces a huge amount of energy. Actually, it's less energy than a Mars bar, but there's so much hydrogen in the sun that altogether that energy output is really, really large, and it heats us very effectively, like today. That's a star for you. This is a first star done with a PowerPoint filter on the sun, and that's because we haven't observed them directly yet. And the difference you can see firstly is that it's blue. A blue star is hotter. So you might be familiar with the color temperature range within stellar evolution, but a blue star is much, much hotter. And the first stars were much, much hotter. They were about 1 million Kelvin, Celsius, whatever you want to say, on the surface of the star compared to our sun, which is about, around about 6,000 Celsius and change. So it's much, much hotter. And the reason for that is partly that it is much, much more massive. Now, a first star, according to our simulations, show that we can expect them to have been around 100 times the mass of the sun, if not 1,000 times the mass of the sun, some very recent simulations have indicated. And when you get something that is so massive, basically the fusion reactions are much, I wish I put a different slide in here. Basically, in the very early universe, you can't cool down gas clouds as efficiently because you've just got hydrogen and helium. And what you need is kind of the heavier elements to carry out a lot of the heat and the light, but they can't do that in the early universe. And so what you get is much larger gas clouds that collapse into a much larger star, and because it can't cool down efficiently, it's a very, very hot star, and also very, very massive. And the problem with being very, very massive when you're a star is that you're not going to live very long. And that's because even though you have lots more actual mass of fuel or hydrogen, you guzzle it down so quickly because of kind of like the gravitational pressure on you, and you're trying to counteract that. And so you fuse your fuel at incredible pace, so that actually you would burn out as a first star after only 1 million years, which is teensy tiny compared to the sun's lifetime of around 9 billion years. Now, if you're a first star that came around 13 billion years ago, as we say, we're not quite sure, but in that first billion years somewhere, and you lived 1 million years, then you can tell that there is going to be a problem in terms of observing these in the local universe. They are more than likely all extinct. And so these first stars aren't just a star like we see next door. It would be very much easier just to study our sun. These first stars are an extinct species. They are new and yet old, and something that you cannot create in the universe today because it has changed so much. And the reason that it has changed so much is because of these first stars, and because of how they have changed the universe. Now, what we see here are 3 generations of stars, which, as we are mostly astronomers here, I think you've probably heard of them as population 1, population 2, and finally on the right, population 3. Now, population 1 stars are your young stars like the sun, and what we say are they are very metal rich. I'll get onto metals in a minute. In the middle, we've got population 2 stars, and these are slightly less metal, so we call them metal poor. But then you finally got the population 3, or first stars, it's just easier, which we call metal free. Now, might be all familiar with it, but this is the chemical periodic table of the elements, plenty there to look at. you've got hydrogen, you've got helium, and these are the main elements that anybody cares about as an astronomer, because it makes up what, after the Big Bang, hydrogen made up around what, 70% ish, helium was like 27 or something, you know, whatever. Everything else was garnish. And so this is what the astronomers do. And we round up the periodic table, just as we round up distances and times, like I've been doing, like billion years or so, whatever. So we have hydrogen, helium, and metals. So when I say metals, I mean any atom that, or molecule that is larger, any element that is heavier than helium. So when I say here metal rich, metal poor, metal free, I mean metals free because it's composed only of hydrogen and helium. And that's because in the early universe, there was only hydrogen and helium. But what happens is that the first stars begin to fuse these elements into ever heavier elements. So we get hydrogen, helium, lithium, beryllium, boron, carbon, all the way up to iron, where a star basically judders to a halt when it gets to iron because of an energy issue. And so when the star does die, it flings out all of the heavy elements that it has managed to fuse within its lifetime, and it pollutes the surrounding universe. It seeds the surrounding gas with all of these heavier elements. And so immediately you have a universe which has gone from metal free to metallic to polluted. And so you physically cannot create a star in that area that is metal free, because it's got to be created from that kind of same dust cloud, that same gas. You can't filter it out, so it's there. And so you have this evolution over time, this generational family tree, if you will, where you have your metal free stars, and then you produce your population 2 stars of stars that have got you know, really incorporated those metals, and then they add even more metals, and supernovae add heavier elements, and suddenly you've got metal rich stars like the sun. But metals still only account for, I forget, but a few percent of the entire proportion of the sun. It is still mostly hydrogen, but we still metal rich. And so it's the first stars which changed the universe from something very dark, very black, very boring, to a universe full of diversity and color, full of just the most amazing structures. Like you can see 2 galaxies colliding at the bottom. And it just amazes me that this isn't an artist's impression all the time. It's the second print that I've got on my dining room wall. Sorry, there's no dignified way of doing that. As I've said, you've got the Hubble Deep Field image here, which you can see a lot clearer than I just showed you. And you can see, you know, like, anyway, time limit. So we know that the first stars are extraordinary. So we know they were them. We know that they're well worth exploring for whatever moral or scientific reason that you'd like to do. So how do we go about observing them? We have our first star approximation here, and now we want to really start to fill in this time. So the first thing we're going to do is we're going to look back in time. And as I've said, this is something that is very, very familiar to astronomers, in that all we need to do is tune into light that has traveled so far that it is incredibly old. And so we see its source as it was that age ago. Yeah. And so that's what we do. That's what I do. We tune into light which has traveled 13 billion years from the first stars. And it's been stretched by the expansion of the universe. It's lost a lot of energy running against the treadmill, and it's been stretched into much longer wavelengths over that time. And so when we receive these wavelengths from 13 billion years ago, it's not the light that you might expect. It's actually radio light. And so I'm a radio astronomer. and I use radio telescopes. It sounded like I was at AA. I'm Emma and I'm a radio astronomer. But yeah, anyway, I'm a radio astronomer, and this is what we do. We use radio telescopes to tune into the light from way back when. And radio telescopes look quite different to Hubble and any optical telescopes you might have in your home, in that they look a little bit like the radio antennas that some of the older ones like me might remember putting on the top of their houses to listen to television. And they're a jumble of wire and metal, and there's nothing special about this metal. It's not NASA made metal. It's metal you can buy down your DIY hardware store. And actually I've put up one of these, and I think it costs around €100 without the electronics, but you know, that's the materials. This is cheap fun stuff. And so what we do is we get, and there's lots of different types of antennas. This is the one that I work with. It's as well, this is the low frequency array in the Netherlands, and it's just stuck in the middle of a nature reserve. And it's these little bow tie antennas, and they're all underneath this tarpaulin. And it's okay, you can feel underwhelmed, because yes, it is not as exciting as a clean room rocket launch from NASA with Hubble. But what is amazing is that I'm going to turn it on its head, with just that piece of metal in a field, without NASA, without a clean room, we can tune into light 13 billion years ago, which is further. And the way we do this is that we create a gigantic telescope, much larger than you could ever create with, for example, a single dish or a single mirror. And we spread 1,300 of these antennas across the European region, and we connect them all up either by Wi-Fi or by fiber optic cable, and we collect all of the data from these antennas that they are seeing, and we put it together in a really, we correlate it in a really, really complicated and clever way, which interferes the light literally, so that we can tune in to the right direction and the right wavelength of light. And there's many, many different telescopes that are trying to find the first big detection of this era all over the world. And so it was with great surprise that I've given this talk for 10 plus years, and this has always been my not this talk, but the talk on the race for the final detection, and this has always been my slide for that, because these are the main telescopes. So it was with great surprise in 2013 when I got rung up by the Guardian and said, can you comment on this story? It's embargoed, we need it by tonight. And they handed me this paper, this Nature paper, and it was that astronomers have detected the signals from the first stars in the universe. I was like, oh crap. And then I actually read it, and I read this paper, and I mean, my husband will attest to this, I literally bounced around the house in excitement and pure joy, because yes, it was a competitive thing, but it was a happy competitive thing. And the fact that the first piece of information had been found, it really felt like somebody had drilled the hole in the tomb wall of Tutankhamun. You know, somebody had finally done it, and we could finally start to look through. And they did it with not 1,300 antennas spread across the European region. They did it with one. They did it with one table-shaped antenna in the Western Australian desert. Very cheap experiment set up by like 6 people. And what they did was they put it in a very quiet area. It's like 50,000 square kilometers and has a population of 115. So really, really quiet, which you need for radio. And what they did was that they didn't try to be too clever like we are still trying to do, which is what we're trying to do is kind of look at the footprint of the first stars by taking the measurement of all of the surrounding hydrogen and actually build up a picture. So we were basically trying to build up pictures. What they did was say, look, while we're waiting for that, let's do something a bit simpler, which is they just took the temperature of all of the gas, all of the hydrogen that was surrounding the first stars, that was within the universe, because they very correctly theorized that the universe is nice and cold early on, But when the first stars appear, they produce heat and they produce light and lots of heat. And so it will necessarily heat up all the hydrogen. Now, this hydrogen sends us photons of a very particular wavelength, 21 centimeters. You might have heard of 21 centimeter radiation. It's very important in the radio world. And that is, well, for many reasons, but the 21 centimeter radiation from the first stars, it gets stretched to a wavelength of around 2 meters. And as you saw, that metal table was, you know, around 2 meters. So it's really good for collecting this level. And so they looked at when that temperature heated up, when the intensity of that radiation heated up, as they tuned their telescope forwards and back through time. Simple. And that's, oh, did I not put any more on that? That's a shame. Okay, I'll just tell you, which is pretty cool. So they did this, and they pinned down the emergence of these first stars forming to be about 180 million years after the Big Bang, which is great. We've got our first data point. We finally knew when in that billion years they started to form. There's some really weird stuff about this. If there's like this really awkward silence at the end, Tracy can be like, what's that really weird stuff that you mentioned? And we can just fill it. There's some pretty weird stuff going on here. There's the other implications of this. But for now, for this talk, hurrah, we've got our first data point. That's really cool. And with the interferometers like LOFAR, and with what's called the Square Kilometre Array, which we're building around the metal table in the Western Australian desert. But this is instead going to be 130,000 antennas. And actually, this was greenlit for construction 2 weeks ago, after 30 years of planning. And so it's going to be boots on the ground, putting those antennas down very, very shortly. And if we're funded to second stage, it will be 1 million antennas across Western Australia. So we're going to be able to do some pretty powerful stuff. And the idea is not just taking the temperature of a single point in space to figure out that evolution, but taking images of this gas and kind of seeing where the first stars were. So kind of seeing where they've burnt it away. So it looks like a Swiss cheese, basically. We're trying to take a picture of Swiss cheese across time. But how else can we see it? And I just want to cover this really quickly. This is not my area, but it's an area that I follow very closely, partly because it's got archaeology in the title. But stellar archaeology is the idea that you don't look back in time. Instead, you look around you, you look nearby you for the artifacts that have been left behind. And, you know, you might be confused here because I said, well, they've all died out. But very recent simulations in the last 3 or so years, a little bit longer, but it's more and more evidence has piled on that the first stars did form in the central stars in a gas cloud were indeed extremely massive. But what seems to be happening is that the gas cloud fragments around it and sibling stars are formed of much smaller mass. Now, some of these sibling stars, and there's up to 50 in some simulations, some of them in spiral and just get merged. Some of them get kicked out by extremely high velocity kicks, so they're wandering the universe. And some of them just settle down into like a binary orbit of the star. But these stars, these sibling stars, if there is a star or many that have 80% the mass of the sun or less, then these stars will live, for example, for 14 billion years. And that's long enough to still be around in the Milky Way today and in other galaxies. But there's a problem. There's always a problem. And the problem is that you'd think it was quite easy to see these things because they're the only ones without metals in. Yeah, you can just do spectra and figure it out from the light. But the universe back then was very clean. It was very pristine. It was unpolluted. But these stars will have been hanging around the universe for 13 billion years, over which they will have just got camouflaged in all the dirt and dust and metals in the universe. And so a stellar archaeologist's job is literally to say, look, all these stars look really familiar, look really similar. And they have to kind of look at the light from these stars and really try and figure out kind of like is that metal just camouflage, or is it actually really in the star? That's a really difficult job. Oh, stupid animation. And what they don't tell you often about Tutankhamun's discovery is that Howard Carter didn't just stumble across this tomb. He didn't just kind of trip in the desert and go, yeah, I found a tomb. What actually happened was that his patron, Lord Carnarvon, bought a site for him to dig on. And Howard Carter meticulously gridded it. And he started looking and he started digging. And he dug, and he dug, and he dug. And 5 years later, Lord Carnarvon said, that's it. I'm cutting you off. You've had all of my money. You found me absolutely nothing. That's it. At which point Howard Carter says, come on, one more dig. Let me just dig one more season. What do they find? They find Tutankhamun's tomb. Always in the last place you look. And so at this point, they party. But my point here is that I heard a great quote 2 nights ago on at a different event I was on. What was it called? It was an overnight success, decades in the making. This is what somebody said about an event in astronomy telescopes, and I thought that was the clearest I've ever heard it put, which is that things take years, collaborations take decades to figure out, and there are a lot of mistakes along the way. And it's the same with stellar archaeology, is that what they need to do is grid up the Milky Way. They need to figure out where the most likely areas of the Milky Way are to find these kind of stars, and they're getting incredibly close. They've managed to find a star with so few metals in that it can only be a second star, so as in the first descendant of a first star. And from that you can actually tell a huge amount, because you can tell you can tell what mass that first star supernovae was. You can tell how much of it gathered. Not much, but enough. So that's what we're going to do. I think, am I running out of time, Tracy?
No, you can keep going as long as you like.
No, I mean, I've just got like 2 minutes left, so I just want to complete this for people that don't know how we measure metals. So I mentioned spectra early on, and so what stellar archaeologists are doing right now is that they've gridded the Milky Way, and they've said, right, the most likely places we're going to find these are the bulge, which is the oldest part of the Milky Way we know of, and the halo, which is where a lot of the older stars kind of drift to out of the main disk. So they're looking in these places, and what they do is they look at a star that they think looks likely, about the right mass, and they record the light from that star, what we call a spectra. Here, a spectra of visible light. And when you have different elements within an atmosphere of a star, those elements absorb very, very particular wavelengths of light. So, for example, if there's calcium, there'll be well, there'll be more than one, but there'll be a defining wavelength missing from your spectrum. Iron, there'll be another defining wavelength. Carbon, another one. And so what you get is a barcode which tells you what is inside that star, or rather what is on the surface in the atmosphere of that star. And so what we are trying to do, what they're trying to do, see, I'm trying to be a part of them like a football team, like, yay, we won. And they've got the spectra there. And so what they're trying to find is a spectra that the metal lines are so faint, so weak, that they can only be explained by pollution, by camouflage. And so basically they've dusted off the metals to the point where they're really, really confident that this is a first star that's just been hiding, that's in a dusty attic. And that will be a phenomenal, phenomenal thing. And both of these areas of research, both the radio telescopes looking back in time and the stellar archaeology looking for the artifacts, are both really coming to fruition right now. So as I've said, the SKA is under construction right now, and the 2020s are going to be the decade for a lot of this science, and well into the 2030s as well. So we're going to have a lot of really exciting stuff happen. And you just don't know what you're going to get. And that's what makes stellar archaeology very hard in particular, is that there are 250 billion stars in the Milky Way. plus or minus 150 billion. I think Google informed me. I'm not good with remembering numbers, so I have to Google things. But that kind of error bar is ridiculous, right? They can't afford to survey them all. So it really is a case of hoping a lot of the time. It's going to take a while. So we've learned about lots of different things. We're hoping the next decade to say, yay, we have detected them, and do some really incredible science, filling in not only kind of the gap in that first billion years, but using that more complete data to correct what might be incorrect conclusions that we're making about space, about astronomy, about the Milky Way, who knows, closer to now. And yeah, incredible discoveries, tearing down the tomb wall, one brick at a time, and everywhere the glint of gold, I guess. So thank you very much. Yeah, questions?